Okay, so when we left off, we were doing examples such as f sub omega of 3, where we'd take the third element of the fundamental sequence and we'd end up with f sub 3 of 3. Okay, so before we move on, I want to make a distinction here. I want to make a distinction between something we call limit ordinals and successors. Omega is something called a limit ordinal. And with limit ordinals, how we treat them within the fast-growing hierarchy is we diagonalize. A number, such as 3, let's say, is something called a successor, meaning that it comes after something, like 3 comes after 2. Omega has no successor because it doesn't come after any finite number. Now, the reason why we differentiate between these two is we want to know how to deal with them within the fast-growing hierarchy. Like I said, limit ordinals are diagonalized, and successors follow this equation here, which we looked at before. It's the fa of n is equal to n copies of the a minus 1th function of n. We follow this. Now, our next example is going to include both a limit ordinal and a successor, and it's our omega plus 1, basically, that we talked about before. So what happens when we plug this into the fast-growing hierarchy? Let's find out. F omega plus 1 of 3. Well, what's the first thing we do? We have a successor on the outside right here. So that means that we follow this equation here. So let's do that. We have f and n copies, which is 3, of a minus 1. Well, what's a? A is omega plus 1. Omega plus 1 minus 1 is just omega. So we have 3 copies of the f omega function of 3. Let's expand that out. F omega of f omega of f omega of 3. What can we do here? Well, now we have a limit ordinal in the subscript right now. So we can diagonalize. Let's do that. We have f omega of f omega of f of 3 of 3. Now, from previous videos, we know that f3 of 3 is a pretty sizable number. It's 10 to the 10 to the 81. So let's replace that. We have f omega of f omega of 10 to the 10 to the 81. Now, what happens here is pretty interesting because we've finally transcended anything that we could do before. We can diagonalize this, and we're basically taking the nth element of the fundamental sequence again, but this time n is this huge number here. So we're going to take this and plug this into the subscript of f. So we end up getting f sub omega of f, and then putting this in the subscript of this. So this really shows the power of infinite ordinals, and it explains why things like infinity plus 1 are useful, because we can couple the power of recursion with diagonalization to reach these huge numbers, because this here would be equivalent to let's say 2 with 10 to the 10 to the 8.1 up arrows, 10 to the 10 to the 8.1. And we still have one more to do too. We take this huge number here, and then we plug that one more time into here. So we end up f omega of the 2 up arrow with this many up arrows, 10 to the 10 to the 8.1. And then we do this operation, which is equivalent to nesting this within another up arrow, since we have 2 up arrow and then 2 up arrow, 10 to the 10 to the 8.1 of 10 to the 10 to the 8.1 of this whole thing here. Gets a little messy writing it in this way. It's not really a great way of doing it, but just to give you an idea of how powerful something like omega plus 1 really is. When omega just got us f 3 to the 3, f omega plus 1 recursively does this and then diagonalizes it. So we put this in the subscript, put this in the subscript, put this in the subscript, and so on. And omega plus 1 is an important one also, because with it, we can revisit one of the numbers that we did previously and with Knuth up arrow notation, which is Graham's number. If we write Graham's number in the fast-growing hierarchy, it is equivalently, it's approximately, equal to f sub omega plus 1 of 64. And I'm pretty sure this is actually much, much larger than Graham's number. Now, if you kind of want to know the rationale behind this, think of Graham's number before. It started out as G1 is equal to 3, quadruple up arrow 3. And G2 was equal to 3 with G1 arrows. But instead of writing G1, let's keep it in this format here. So we have an up arrow, and then we just write this out again. 3, 4, blah, 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 blah. And then each time we write one of these, we're keeping the original one. So we end up with this kind of like nested up arrow notation here. And then eventually what we're going to get to, blah, 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 is with G64, we're going to have 64 layers of this kind of nested up arrow notation type of thing, blah, 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 blah. And this number of layers is really the power of the function. This is where the main value of the function comes from. And if we kind of relate this to the fast-growing hierarchy, the same kind of thing happens. If we have f omega plus 1 of 64, what's going to happen is n is now our 64, so we're going to have 64 copies of the f omega function. So we're going to have f omega of f omega of f omega, blah, 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 64 times of 64. So our first term in this is going to be f64 of 64, which we can roughly put as 2 with 64 up arrows, 64. And then we're going to put this into the subscript of each one all along the line. So we're going to end up with the same kind of thing. We're going to end up with 64 layers of this nested up arrow type of thing. And the only difference really is that in this case, the starting point was 3 quadruple up arrow 3. And in this case, the starting point is 2 with 64 up arrows, 64. So even though this is a 2 and this is a 3, this is going to be vastly, vastly larger or whatever. So actually, yes, like this, this here is going to be much, much larger than Graham's number. So already we've reached the maximum point that we could reach with Knuth up arrow notation. And it's just going to go further and further from here. I'm going to leave that for the next video, though.